Okay, so this video is going to be about doing some example problems for VSEPR and when we have 5 and 6 groups. Okay, and these are 5 or 6 electron groups around the central atoms. So the first example that I want to do, so my pen is working, so first example I'm going to do is the molecule SF4. Okay, and at first glance, you might be saying, well, how does this fit in with 5 and 6 electron groups? But that will become clear. So the first thing we have to do when we want to do VSEPR, and, I will just say at any point, if you want to pause the video and kind of figure out what the shape of this SF4 molecule is going to be on your own, you can certainly pause the video, figure it on your own, and then restart. So if you'd like to do that, feel free to do that. Okay, first thing we have to do, first step, is draw the Lewis structure. So I'm going to draw my molecular skeleton. So the sulfur is going to go in the middle. The fluorines go around because fluorine is never the central atom. And then I have to do an electron count. So sulfur has 6 electrons plus, right, there are 4 fluorines. They each have 7. And so when I go ahead and add this up and I say, okay, 4 times 7, so 4 times 7, that's 28 plus another 6. So this should have 34 electrons total for valence electrons. And I'm going to go ahead and put them in the way. So first draw the bonds and then do the octets on the outer atoms. So I will do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And I've only got 32 electrons. Now the fluorines being in that first full row of the periodic table, they can't take any more electrons than 8. So that last pair of electrons to get to 34 has to go around the sulfur. So this is the final, this is an exception to the octet, right? Because now sulfur has 2, 4, 6, 8, 10 electrons around it. So it's got 5 electron groups, right? So 1, 2, 3, 4 bonds in a lone pair. And I'm going to go ahead and write that down. So sulfur has 4 bonds, right? 1 lone pair, right? So a total of 5, right? 5 electron groups. So my base shape here is going to be trigonal bipyramid, right? But my actual shape is not going to be that, right? So I've got to think about a trigonal bipyramid, but I have to think about it as a trigonal bipyramid that's lost a bond. The actual shape here, and again, right, when I think about a trigonal bipyramid, actual shape I'm going to say is different. And so when I think about a trigonal bipyramid, I think about a trigonal bipyramid, and I'm just going to go ahead and give myself a little more space. So I'm going to add a black slide here. And so when I think about trigonal bipyramid as the base shape, if it had all 5 bonds, right, it would look something like this. I'd have 3 in sort of a T shape. I'd have 1 coming out at me, 1 going in the back. So that's what, with 5 bonds, it would look like. And remember, this is the one where I have different bond angles. So I'm going to go ahead and use my pen, right? These have 120-degree bond angles. And then I'll use a different color up here. There's also these 90-degree bond angles. And, there's a video on which ones you take out. But essentially that lone pair, right? I've got 4 bonds in a lone pair, right? The lone pair wants more space. And so, right, we're going to take away one of those 120-degree bonds, right, and replace it with a lone pair, right? And so essentially what's going to happen is, say, one of those is going to go away, and I'm going to redraw that with the lone pair. So for SF6, and maybe actually I will just draw it with the sulfur and the S6, right? So sulfur, and I'll have the fluorine up here, a fluorine up here. I'll put the lone pair over here. I've got a fluorine coming out at me and a fluorine behind. And this is actually the seesaw shape, or some people call this a distorted tetrahedral, right? So that's the other name for it. So this is going to be a seesaw shape. And I just want to be able to rotate this around so you can see it. So I'm going to go back to my other slide. I have the PhET simulation up here. So it's loading. You can either do model complexes, or they actually have this thing to do real molecules. So I'm going to click on real molecules. I'm going to select one of their examples as SF4. So they put it in here. I'm going to say, please show me the trigonal, the electron and the molecular geometry. So, and actually, why don't I make this just a tiny bit bigger? So you can see over here, right, electron geometry, trigonal bipyramid, molecular geometry is seesaw. And I'm going to go ahead and rotate this around. So again, the lone pair is sort of in that position. So I'm going to try to put it like I had it on the other page, if I can get it to cooperate. Right, so this is how I had it drawn on the other page. If you want to see why it's a seesaw, now I will rotate it around and make it look like a seesaw. Right, so this is a little like a seesaw, so you could imagine a person over here, a person over here, right? This is the middle of the seesaw. So this is the sulfur, these are the fluorines, right? A person over here, and this thing, I'm just curious, I'm gonna try. It's easier to do with your model kits, but right, so kind of like see and then saw, like these people would be going up and down. So the answer to this one is, so it's based on a trigonal bipyramid, but the actual molecular shape is different, and the actual shape is going to be a seesaw. Okay, so that's my first example. Let me go ahead, a couple slides here. So my next example that I want to do, so example number 2, I want to do xenon F4. And again, you might be saying like, wait a minute, xenon F4, how does that fit in with the 5 and the 6 groups? But we'll see that in a minute. So xenon is going to have to be in the middle. And again, I have to draw the Lewis structure first. And I will just remind you, if you want to stop now, right, draw your own Lewis structure, go ahead and figure out what the shape is on your own. Feel free to do that. So if you want to pause the video at any point, restart it. So first we're going to draw the Lewis structure. So that's my molecular skeleton. Now I have to figure out how many electrons I have. So xenon, being a noble gas, has 8 valence electrons. There are 4 fluorines. They each have 7 electrons. And so when I do this math, I say, okay, 4 times 7, that's 28, plus another 8. This actually has 36 electrons to go in the structure. I'm going to go ahead and do that. So 2, 4, 6, 8. Now I'm going to complete the lone pairs. So 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I've got to put in up to 36, right? I've only at 32. So the xenon's going to get actually 2 lone pairs around it. And again, this is an expanded octet. So I'm going to have 1, 2, 3, 4 bonds, 2 lone pairs. So, I want to do this. So I have 4 bonds around the central atom, right? 2 lone pairs, right? So this is a total of 6 electron groups. So my base shape, right? They call it the electron geometry in the PhET simulation, is going to be an octahedron, right? So octahedral base shape, right? And now I have to figure out the actual shape. Okay, so I'm going to go ahead and do that work on the next slide. So, all right, I'm going to draw an octahedron here and then we got to figure out like which bonds are going to go away and be replaced by lone pairs. So here's my octahedron, right? All are at 90-degree angles. This is a very symmetric structure. Okay, right, so my goal, right, is get those lone pairs, LPs, right, away from each other. Okay, so first things first, maybe I'm going to use my eraser tool this time. So I just have to take away one of these bonds like that, right? I'm going to fix the central atom and I'm going to put in a lone pair there because all of those bonds are equivalent in the octahedral to begin with, right? I'm just going to go ahead and just pick one and take that away. And now I've got to figure out, okay, do I take away the second bond from this square plane or do I take it away from here? And again, my goal is to get those lone pairs as far away from each other as possible. So I'm going to go ahead and get my eraser tool out. And to do that, you know, if you want to pause the video and guess, right, like, are we taking it away from one of these 4 equivalent positions or from this one? I've got 2 choices. And the one that's going to get those lone pairs as far away from each other is this bottom one. And so it's going to look something like this with the lone pair here. And then when I think about what does that shape actually look like, I've got 4 bonds, right? They're in a square, they're a plane. So the shape, right, helps if you can write. The actual shape of this is going to be square planar, right? So that's the actual shape. You can call it the molecular shape if you're following along with the PhET videos. And actually, I'm going to go do the PhET video now. So I'm going to go backwards. I'm going to try to make this load again. So they bring me to PhET. I'm going to go to real molecules. And actually, you know what? I think I'm going to make this a little bigger if I can and not take up any space. Okay, so let's go ahead and click real molecules and look at their example. And sure enough, XeF4 is one of their things, right? It's based on an electron geometry. Its base shape is an octahedral, right? But the actual shape is a square planar. And you can see it. Those 4 atoms are in a plane, right? The 4 bonds, right? So here's my xenon in the middle. These 4 are the fluorines. Right here, my 2 lone pairs. And this is the shape that gets those lone pairs as far away from each other as possible. And I guess I'll just do this so you can see it looks like a square. Right? It looks like a square. The 4 bonds are in a plane. And I'll show the bond angles. So, right, they are 90 degrees like you would expect. Okay, so that's the xenon F4, and that's the end of this video.